All right, let's talk about inverse functions. Okay, on the simplest level, an inverse function, all that really is, let's take a look at this to get an idea of what we're doing here. All you're really having to do here is, obviously the f of x is kind of like your y. You are going to switch the x and the y. So where the y is or where the f of x is, you're going to write x equals. And instead of a y, or I'm sorry, instead of an x here, you're going to put a y. So we switch these around. And now what we want to do is we want to solve for y. We want to get y all by itself. Just like y was all by itself here, we're going to get y all by itself here. All right, so no big deal. We're going to subtract 3 from both sides. I get x minus 3 equals y plus 2 in parentheses cubed. All right, so I have to get rid of that cube, so I'm going to take the cube root of both sides. All right, that cancels this and this out. So now what do I have? Now I have the cube root of x minus 3 equals y plus 2. Last thing I got to do is subtract 2 from both sides. And so now I have, I'm going to put the y on the left side, the cube root of x minus 3, nope, not plus, minus 2. And so what we could say this is the inverse. We'd write it like this, f negative 1 of x. So if this is f of x, the inverse function is this. Okay, that's what an inverse function is. So an inverse function really, like, it just undoes the other function. So like, if I was to take this whole thing, I know it's equal to y, but if I was to take this whole expression here and plug it in for x, what we would have is we would have everything cancel out to that we just get x. For example, like we've done inverse functions before, you just never really called them that. Like if I had x plus 2 and I subtracted 2, that would just give me x, because the plus 2 function and the minus 2 function are inverses. Or if I had x, if I had 2x and decided to divide both by 2, I'd end up with x. Right, so the 2 times x is a function, and then this you could call this an inverse. Or one of the most common things you've probably seen is if you got a square and a square root, you end up, right, the square is a function and the square root is a function, and they undo each other, right? In all these cases, what you have is you have things like undoing each other to get back the x. These are all little inverse functions. And so this is officially an inverse function of, obviously more going on than just a square or just multiplying or adding. Okay, so here we have the graph. Well, what would this thing look like graphically? What would the inverse look like? Well, the first thing you need to know is it's always going to reflect across this line y equals x. So I'm going to do my best to just kind of sketch this out. There's the line y equals x. Well, if I could just reflect this over here, I'm going to get the inverse function. It's always just going to be reflected across the line y equals x, not across an x or y axis, across this diagonal line. So what would that look like? Well, let's look at a couple points that I know for sure, right? I got this point here, looks pretty solid. This also looks like a point. This also looks like a point. And this also looks like a point. So to be accurate, when I go to write the reflection, I'm just going to, literally all I have to do, if I think about this, this is negative 3, 2, this is negative 2, 3, and this is negative 1, 4. Oh, and this one down here is negative 4, negative 5. Remember, all we did is switch the x and the y's. Same thing's going to be true here. So I should be able to find 4, negative 1, 3, negative 2, 2, negative 3, and negative 5, negative 4. And if I kind of like connect these dots here, boom, you can see how this graph is an exact reflection across the line y equals x. This blue graph here is this graph right here. It's the graph of this. The inverse graph will always just be a reflection across the line y equals x. That's it. Let's think about what that means here for these points, right? Like I listed off these points. Maybe I should have done this first, right? But we knew that we had the points negative 1, 4, negative 2, 3, -3, 2, -4, -5. And when I went to write the inverse, all I had to do was just flip them. Literally flip the x and the y. Right? That's literally what I did to find all these points here. So you can make a table and literally flip them, or you can flip them graphically if you're trying to get a graph. But that's all it is. So let's look at another one here. Okay, I got f of x equals -2 square root x minus 3, and then that whole thing, you're going to subtract 2. So we want to get the inverse first. Let's just try this. Actually, before I do anything, I want to talk about the domain. And what we can tell by this domain, just by looking at it, is remember that we are not allowed to have a negative value in the square root. We can't have anything negative. Like I can't have a -1. And so basically everything that's in the square root, right, has to be greater than or equal to 0. So we could start off by saying, hey, the x minus 3 here has to be greater than or equal to 0. That's just how you're going to find the domain. And then if I add 3 to both sides, I'd get that x has to be greater than or equal to 3. And there's a few ways we could write it. I could write it just like that. Or I could say, hey, since x has to be greater than or equal to 3, I could use interval notation. I could say, hey, it has to start at 3, and it can go up to infinity. This is a way of saying it listing all the values from 3 to infinity. This bracket means that we include 3. The parentheses means we don't include infinity, but that's because infinity is not a real number. So parentheses are for numbers that we don't include. Brackets are for numbers that we do include. We'll do the range after we graph it. I just wanted to show you how you can quickly tell the domain just by looking at it. You got to look and say, like, okay, what would cause this function to break? And any negative inside here will cause this function to break or not work or not be able to graph. So you just say, okay, well, that means I have to restrict this, or I have to say the domain has to be greater than 0. This part inside the inside the square root has to be greater than 0. And so once you do that, you can get a domain for x pretty quickly. All right, let's work on actually doing the inverse function now. Remember, I'm going to flip the x and the y. So I'm going to write x equals -2 square root y minus 3. I keep wanting to say plus, minus 2. And I'm just going to do algebra and get the y all by itself. So the first thing I'm going to do is I'm going to add 2 to both sides. So now I have x plus 2 equals -2 square root y minus 3. Next up, I'm going to divide both sides by -2. Get these to cancel out. So now I have x plus 2 over -2 equals the square root of y minus 3. And next I'm going to do is I'm going to square both sides. And this is what I would actually do here. When I square x plus 2, I'm just going to leave that as x plus 2 in parentheses squared. But on the bottom, I'm going to go ahead and square that -2 to make it 4. And leaves me with y minus 3 over here. Last thing I got to do is just add 3. So I'm going to write 3 plus. And essentially, I have the inverse function right here. That's f of -1. By the way, really careful here. This doesn't mean you're used to -1 exponent. Let's go over here and talk about this. You're probably used to like this, meaning this, right? But that's not what it means in this context. And in fact, usually we would put the -1 here. That means the inverse of f of x. Not exactly the same language. So just know in the context of function notation, this -1 means inverse. In the context of a variable, a -1 exponent means reciprocal. A little bit of confusing there, but you got to understand there's different contexts. Just like actually here, in the context of domain and range, this right here means like an interval. It's called interval notation. But if I wrote 3 comma a number, let's say it wasn't infinity, you might think that's a coordinate on an xy coordinate. Again, it has to do with the context. So context matters for knowing what we're looking at. Okay, let's try to graph this one originally right here. Well, we're familiar with this one. I'm going to zoom in. We've done this before. I'm just going to go up here. If I was just simply graphing the square root of x, right, y equals square root of x, it would look something like that. So how does this one change? Well, this one changes because we know the h value is 3 and the k value is -2. So we know this thing is going to shift over 3 and down 2. So I'm going to go ahead and say, okay, over 3 and down 2, that'd be right here. And then we know the negative is going to reflect it. Right? This negative is going to reflect it. And the negative 2 is not only going to reflect it, but it's going to make it grow a little bit. So it's going to do something like that. Okay, so if this is the original, if I was to reflect it down, stretch it, or shift it over first, and then reflect it down and stretch it by 2, it's going to look something like this. You can always just make a t-chart of x's and y's, plug that in, you get some points. Okay, well, we already know we got this line right here of y equals x. And if I was to actually graph what I have right here, you might recognize this. Let me rewrite this in another form. We could say that this is like saying 1/4 x plus 2 squared plus 3. You might recognize that as this form right here. Oops, that's supposed to be a k. We call that vertex form of a quadratic. Now, if based on that, this should be a parabola, right? This should be a parabola. So let's go over here and let's see what that parabola would be. The parabola would have a vertex at -2, +3, and the a value is 1/4. So we could sketch that, no problem. So let's go over here and try to sketch that. Again, -2, I'm just going to write it. The vertex would be -2, +3. So -2, +3 is right here. It's going to stretch out. And it would look something like, I'm going to do dotted lines for now, and I'll explain to you why. Something like that, okay? Well, that's not really a true reflection because we know the square root only has like half a parabola, right? Like the square root, if it was a full sideways parabola, we'd have a parabola here, but the square root function only has half of it. So the inverse can't be this whole thing. The inverse is really only this part. Okay? And this part over here doesn't exist as part of the inverse function. So how can we know that? How can we account for that? All right, so let's go back to this domain thing that we were talking about. So we established the domain for the x has to be when x is greater than or equal to 3 or between 3 and infinity. And once we sketch the original here, maybe I should like highlight this. Let's say green, green. Maybe I should have done this in green as well. Okay, we can see pretty quickly that the domain is 3 to infinity. The range is going to be negative, range is y values, negative y values all the way up until and including -2. So how can we write that? We could say, okay, we're going to go from -infinity to -2 and including -2. Here's the thing that you have to remember with an inverse. If you have a domain and range with the original function, these must flip to the inverse, to the inverse function. And here's what I mean by flip. Literally, they swap. Okay, so now the domain for the inverse function must be -infinity to -2. And the range must be from 3 to infinity. So because the domain can only go to -2, right here is -2, right? I know that it cannot go past right here. It could be included here. It could be equal to 2, but it cannot go past. So this is important. That's how I know this part over here is not actually part of my inverse function. So we have to restrict it to this domain and this range because sometimes the equation we'll come up with would represent more than the actual inverse function itself. So yes, this is the inverse function, but with this domain and range, it's very, very important that the domain and range carry over. Because if you were to include this part, you'd be inaccurate. I hope that makes sense. We'll talk more about that in class. All right, let's keep going. So Does the function have an inverse? Do these have an inverse? So we're going to talk about these real quick. Well, you're used to saying, hey, does this pass the vertical line test? I got this little lightsaber thing to use my vertical line. Here's my vertical line. And yeah, this passes a vertical line test. So we're good, right? We're good. But remember, when we're talking about an inverse, what would the inverse look like here? The inverse here would look something like this. And now would the inverse pass the vertical line test? No, it would not, right? No, it would not. So what we're going to do is the inverse, to test for inverses have to pass the vertical line test, or determine if it has an inverse, vertical line test, and the horizontal line test. You have to do both, okay? So you can just look at the original and you can just say right here, does that pass the horizontal line test, or does it intersect it at only one spot? No, it intersects it twice on a horizontal line. Therefore, no, this does not have an inverse, okay? And it has to do it for both. It has to pass both, because it has to be a function to pass the vertical line test, and then it has to be, the inverse has to pass, to see if it has an inverse, it has to pass the horizontal line test. All right, so we go here. Does this one pass the vertical line test? Vertical line test, yes. Horizontal line test, no. So it's not going to work. Okay. All right, the other thing that we have to have mapping. Let me explain what that means. Like, you're used to, for every individual x value, let me change my little lightsaber back. For every individual x value, you should have only one y. And that's fine. That's fine. But what if we're asking about the inverse? Well, for the inverse, we want to do this thing called mapping. Let me show you. So let's list all of my x values. -2, 0, 2, 5. And over here, all my f of x values. And I'll list them in order. You could also call them y values. -5, 5, and 7. So we got these two groups, okay? And if I mapped all these, okay, -2 gets me a 5. Okay. 0 gets me a 7. Okay, that's all right. 2 gets me a -5. Okay, no problem there. And 5 gets me a 7. That's where we have a problem right here. Look. Both of these give me the same thing. We don't have a one-to-one relationship, and therefore this cannot have an inverse, right? Because if I was to switch these, if I was to say, hey, let's make these my x values and let's make these my y, we would now have, plugging in a 7, we'd get out both a 0 and a 5. So this does not have an inverse. So all three of these are no, they do not have an inverse. Let's go to the next page. So one-to-one function passes the vertical line test and the horizontal line test. We just covered that. I talked about the mapping on the previous page, so I'm not going to show you that again. But if you have more questions, you could ask me about that in class. But there's really only two conditions where we can get one-to-one. Okay, the only way you can get one-to-one, two conditions, is it is either always increasing or always decreasing. And you have to be careful of this. So I'm going to kind of sketch this out. So if it's always increasing, it could look something like this. But you got to be careful, because like, you can't even get a flat. If I get flat at all, then that means when I go to do the inverse, I'll have something going straight up and down. I'll have 2 points right above each other, and that means it won't pass the vertical line test. We can also have always decreasing, right? And so we got to be careful, but it could look something like this. Obviously, these are not like perfect. So like even here, I kind of messed up, right? Because like it's decreasing, and right here it came back up. So that would be wrong. And even here it came back up a little bit. But the idea is that it's got to always be decreasing. So technically, this would not be a good example right for these parts. So ignore that, but just making sure it's always decreasing. It can have some curvature to it, but it can't come back up, because if I really, really wanted to be critical here, and I zoom in, right, that doesn't pass my horizontal line test. Therefore, it won't have an inverse, a one-to-one mapping. Okay. All right. How do we test if two things are inverses of each other? Here's how this works. Here's the rule. And this, you might want to write this down, put it in bold, highlight it, or something like this. If they're inverses, if f and g are inverses, then f of g of x will equal x, and so will g of f of x. Okay, what does that mean? That means if I took this function, let's get the highlighters out. Let's call this g. If I took this whole thing and I plugged it in for x here, I should get out, when I simplify it all down, I should get an x out. If I do not, right, so this is g plugged into f. Or I could also take all of f and plug it into g, it doesn't matter. But if I plug this in, it doesn't simplify down to x and they're not inverses. So let's test this out. Let's actually do this. So what I'm gonna do is I'm gonna write f of x. I'm gonna write f of g of x. We're gonna try this out. So f is 2 over, and then for all the g, I'm gonna write g is really 2 over x minus 3. To put that all in parentheses. And then plus 3. And we're just gonna simplify this all out. And we should end up with just an x if they are truly inverses. So let's give it a try. Well, we really don't need the parentheses much here because there's nothing happening to these parentheses. So I have 2 over x minus 3 plus 3. Those obviously just cancel each other out. Okay. And then I have 2 divided by 2 over x. And remember, anytime we're dividing by a fraction, we could flip and multiply by the reciprocal. And we could actually think of this 2 here as like 2 over 1. So this is the same thing as saying 2 over 1 times x over 2. And sure enough, these 2's cancel out. We're left with just x. Voila, look at that. So are these inverses? Yes. Yes. Yes, they are, because when you plug one into the other, you end up with just x. All right. No big deal. We got that. That's how you're going to test for something to be an inverse. All right, last thing here. Let's bring the pain. Let's do it a rational function here. We could do this. No big deal. So let's find the inverse. Let's find the inverse of this. Let's start by swapping the x and the y. All right, we got to try and get the y all by itself. Before I do that, I'm going to have to just like get rid of this fraction. So I'm going to multiply both sides by y plus 4. So what do I have? I would have xy plus 4x equals 2y minus 3. All right, let's add 3. Add 3. Let's also subtract this xy and subtract this xy. What would that end up with? So these would cancel, these would cancel. I'd have 4x plus 3 equals 2y minus xy. Okay, at least all the y's are on the same side. Now we got to solve for y. I'm gonna factor out a y here. So I'd have y 2 minus x equals 4x plus 3. And then I could divide both sides by 2 minus x. And that would cancel that out. So then I'd have y equals 4x plus 3 over 2 minus x. So we can do it. We just found the inverse of this function. Couple things to keep in mind. Like, I actually multiplied out the denominator. That was my first step, is just let's get rid of this fraction thing. And then once I did that, I distributed and just started moving terms around until I got the y's on one side, x's on the other, and then slowly did the work to get the y all by itself. All right, factoring is key here. So there's my inverse function. Right, if this is f of x, then the inverse function of x would be 4x plus 3, 2 minus x. And hey, if you really want to, you could take this whole thing, plug it in for x, and see if it simplifies down to just x. All right, that's it for this video. It's been fun. See you guys next time.